Well, now I'd like us to talk about acceleration, and we're going to use the relative equation to analyze some acceleration. All right, so we know from our fixed axis analysis that we know that there are two components to acceleration. If an object is rotating about a and it has some omega in this direction, and maybe it's accelerating and has some alpha in that direction, we know that there's a tangential acceleration, which is r alpha, and that's going to be positive in the direction of positive alpha. So in other words, if it's accelerating in this direction, the tangential acceleration will be going that way. There's also a normal acceleration, which is r omega squared, and this is positive toward the point of rotation, so it always points in. So curiously, again, if omega is going this way, if it's accelerating, a tangential acceleration will be going that way. However, if it's decelerating, in other words, if alpha is going this direction, the tangential acceleration would go in the other direction. Acceleration in the normal direction, however, will always point toward toward the center, whether omega is going this way or whether omega is going that way. The acceleration in the normal direction always points toward the center of rotation. All right, so we have a relative equation for acceleration that we've used before. We're going to say the acceleration of b is the acceleration of a plus the acceleration of b with respect to a. And we know that there's two components to that acceleration. There's a normal component and a tangential component. So we're going to say that the acceleration of b is the acceleration of a plus the acceleration of b with respect to a in the tangential direction plus the acceleration of b with respect to a in the normal direction. Now, if we have fixed axis rotation, we know that acceleration of a is equal to 0, and so acceleration of b just has two components. However, in the general case, when acceleration of a is not equal to 0, then it's going to have, the acceleration of b is going to have components in all three of these, could be all three components in perhaps three different directions. All right, so here's just a little picture of that. Let's say that a is accelerating in this direction. We have an alpha and omega in this direction. We may have an acceleration of a in that direction, which is the same as, so this is point B up here. Acceleration of b will have an acceleration of a component, a normal component due to the omega squared, and a tangential component due to the alpha. All right, so we're going to use the cross product equation just like we did with the relative velocity equation, and it makes the math happen easier in one step. And so what we'll say is that the tangential component is the r alpha component is going to be alpha cross r of b with respect to a. In other words, the distance between b and a, and we'll use the I and j components there and to do that cross product. The normal component up here is the r omega squared component, and that will be minus omega squared r of b with respect to a. All right, we're going to use that in a couple of times here. All right, many students get confused on how to draw the arrows when we're drawing our picture and writing the equation. So the main thing is to make sure that the arrows and the SIGN, the sign in the equations, are consistent. So first of all, we'll define our positive i's and j's. Let's say that in this case, the I is going to the right and j is going to this, so that would be x and y. All right, and what we've got here is just a little picture of a object that is falling under its own weight, and it's falling down this way, this end of the object. This is a kind of a roller on the end of a stick or a ladder or something like that. But at any rate, in the problem we'll suggest that the velocity of b is going in that direction, and then the velocity of this end, a, would be going down that way. We may say that it rotates in this direction because it's going to go rotating in the counterclockwise direction, so we'll call that omega. Now we may also say that the acceleration of b is going in this direction and the acceleration of a is going in that direction. Acceleration of a is going down in that direction. So all I'm saying is just make sure that whatever direction you draw your arrows, it has the same sign in the equation. So we also need to make sure that omega and alpha are positive in the counterclockwise direction. That'll be positive k. So let's just write the equation and make sure we're consistent here. Let's just say that velocity of b is equal to the velocity of a plus the velocity of b with respect to a. So if the velocity of b is going in the positive I direction, we'll just write that as positive I. If velocity of a is going in the negative j direction, then we just need to make sure that it is a negative j. And then we'll keep our omegas, and then omega, as we've drawn it as a counterclockwise direction, we need to make sure that that is a positive omega k when we do our cross product. Same with acceleration. If we say that b is going in the right direction, I'll say that is positive I for acceleration of b. If it's accelerating in the negative j direction, then in the equation it needs to say a negative j. And then again, if we define alpha as going in that direction, or we suspect alpha is going in that direction, then when we write our cross product, we'll just say that it is positive alpha k cross the r of b with respect to a, and then the other terms. All right, so let's do a little illustration of how to draw our arrows and making sure our equations match that. But let's say we have a stick here that's 3 feet long. It's accelerating, or at least the bottom piece of it, the bottom point of it is accelerating in that direction. Let's say that it is the acceleration of A is going that way. We're going to say that it's also rotating in this direction. It's got an omega, and it's accelerating in that direction. It's got an alpha, and we're going to say omega is 5 radians per second and alpha is 1.5 radians per second. We want to find the acceleration of b using the relative equation. So we're going to write the equation. Acceleration of b is equal to the acceleration of a plus alpha cross r of b with respect to a minus omega squared r of b with respect to a. Okay, now let's just fill in the gaps and see where we are. So I'm going to say that that's equal to acceleration of a, and then we have an alpha, and we're going to say that it's going in this direction, which is negative. It is clockwise, so that would be minus k, and alpha was given as 1.5, so that would be 1.5. We're going to cross that with r of b with respect to a, and b with respect to a is where b is if I'm standing on a, and so b is up 3 in the j direction, so I'll put 3j, and that's all in parentheses like that, minus omega squared, and omega was given as 5 squared, or as 5, and we're going to square that, and then b with respect to a is going to be 3j. And so let's do the cross product. We're going to say the acceleration of a plus k cross j is negative I. But I've got a negative sign here, so that's going to be 1.5 times 3 in the I direction. So 1.5 times 3 I direction. Right? K cross j is negative I, but got a negative, so two negatives make a positive. Then I'm going to say minus 5 squared times 3, so that's 5 squared times 3, or 25 times 3, in the j direction. So now I have an equation for the acceleration of b that is all in vector form, i's and j's. If a had I and j components, I would just put those in there and multiply that out and add them all together, and I could find out what the total acceleration of b. So again, this is the alpha component, the r alpha component. You can see that it's going in the I direction, which would be in that direction. And this one is negative in the j direction, so again, it's going in the direction. So this is the normal component. All right, so let's do a problem here, and we'll just make sure we're tracking. Here's a problem from our textbook. I changed the values a little bit just so that I can make it a little more interesting. But let's just say this wheel is rotating in this direction. It's driving this arm, which is on the top of the wheel. The arm is connected to this piston, which is going to be going in this direction. We don't know which direction it's going to go necessarily, but the piston is constrained to move inside this cylinder type arrangement, so it's going to be going that way. So we're going to say that the omega of the wheel is 6 radians per second, alpha of the wheel is 5 radians per second squared, and what we want to do is find the velocity of c. We want to find the omega of bc, this arm right there. We want to find the acceleration of c and the angular acceleration of bc. All right, so first let's write our acceleration equations. We know that the acceleration of b has two components. If it has an omega going in this direction and an alpha going in that direction as well, we know that there's a tangential component of the acceleration of b. So I'm going to say that there's an a tangential going this way, a tangential of b. We'll call it ab tangential. Because there's an omega, we also know that there's a normal component. And the normal component points in, so I'm going to say that that is AB in the normal direction. We know that there's a relative distance between C and B, and so I'm going to say that the distance, or the relative position of C with respect to B is 0.8 in the I direction. So if I'm standing on B, where's C? It's going to be positive 0.8 in the I direction. Now, the acceleration of C. We know C is constrained to move in this direction, so I'm going to say that it's moving like this. I don't know for sure if that's where it's going to go, but we know that it's going to be moving in that direction. I'll define it as positive in that direction, and I'll say that it has a cosine component and a sine component. And so I'm going to list those right there. Acceleration of C is the magnitude of the acceleration, cosine 30 in the I direction and sine 30 in the J direction. All right, that's as far as I can go with the acceleration equation for now. Or the acceleration information. We haven't got quite to the equation yet. Let's turn our attention to the velocity of C and B. So I know the velocity of B. The velocity of B is also going in this direction, and that's going to be r omega of the wheel. So I'm going to say the velocity of B is equal to 0.2, that's the r, and the omega is 6, so it's 0.2 times that, and I'm going to say that is 1.2 in the I direction. Now, how do I relate to the velocity of C? We have a tool. We're going to use the instantaneous center of zero velocity tool to discover that. Again, we know the velocity C is constrained to move in this direction, and I'm going to suggest that it's going in this direction. And so let's use the IC concept to find that out. We draw perpendicular lines from our velocity vectors. So I'm going to say that there's a velocity vector component going up like this. Oops, that's not very straight. Say this is going straight up like that, and let's just say that the IC is way up there and that sort of thing. We can draw some, we can call this my M, and the N, we're going to say M is on this side, and this is N. Now, what are our angles now? If this is angle 30, this is angle 60, which makes that angle 30, which makes this angle 60. If this is a 90 degree, which obviously makes that one, whoops, that one's going to be a 30-degree angle up there. All right, and then this is 90. So now I can use the sine law to find out the values of M and N. So I'm going to say that M over the sine of 60 is equal to N over the sine of 90, which is equal to 0.8 over the sine of 30. Solving that for values of M and N, I can get M is equal to 1.386 on this side, N is equal to 1.6 on this side. Now I know that my velocity of C is going in this direction. I know that the velocity of B is going in this direction. So we know that the velocity of B is equal to 1.2. We also know that it is equal to M times the omega of BC. And omega of BC is going in this direction, BC. So I can say that M omega BC is equal to 1.386 omega BC, and I can see that the omega of BC is equal to 0.8658. That's the omega of the link here. Again, with our relative accelerator, with our instantaneous center of velocity analysis, we know that this triangle now acts like a rigid body that's rotating about the IC, which means that the velocity of C also is rotating about the IC. So I can say that velocity of C is equal to N times my now discovered omega, and I can see that the velocity of C is equal to 1.385. All right, so I've solved for the first two pieces of the puzzle of the velocity. Now let's move to the acceleration equation and see what we can get from that. Your acceleration equation suggests that, or insists that, the acceleration of C is what we're looking for, is the acceleration of B plus alpha of BC, again that's the link, cross r of C with respect to B minus omega squared r of C with respect to B. Now let's do the cross product. Alpha of BC cross r of C with respect to B. We haven't drawn our alpha on the drawing yet, but let's just say that it's going in the same direction as the omega, alpha BC. Okay. So if I do that, that's in the counterclockwise direction, which makes it a positive k. So let's put positive k in our cross product equation. So I'll say positive k alpha cross r of C with respect to B. So that was equal to positive 0.8 I. All right, now if I do that cross product, k cross I is a j, and it's a positive j. So I've got 0.8 alpha in the j direction. That's the value of the cross product. Okay, now I've got all the pieces together that I can put into the relative equation. I'm going to say that acceleration of c is what I defined before up here. So I'm going to put both of those terms in on that side of my equal sign. I'm going to honor the equal sign here. So acceleration of c, cosine 30i, acceleration of c, and again, these are the magnitudes of the acceleration, and these two are the directions. This is going to be the I and the j component. All right, that's going to be equal to the acceleration of b. Well, the acceleration of b had two components, didn't it? It had a tangential component in the I direction, a normal component in the j direction. So I put both of those pieces in there, plus the cross product. So we already solved that for equal to plus 0.8 alpha in the j direction. And then the omega squared component, minus omega squared. I solve for omega squared, or omega up here is 0.8658, so that term is squared, times the, with respect to term of 0.8i, and so I just multiply that out. So again, I'll have an I term here, a j term, an I term, I and j are there. So the way to solve this then is we want to look for the, we're looking for alpha as an unknown, and we're looking for the magnitude of AC, which is unknown. So we combine our i's and our j's. All right, so we'll do the i's first. I'll take for all the I terms out of here, and I'm going to look for, here's one, AC cosine 30. Put that there. Nothing else on this side of the equal sign, so the equal sign goes there. In I terms I'm looking for, there's 1. And here's 1. 0.8658 squared times 0.8 is equal to negative, or is equal to, this is equal to 0.6, and with the minus sign you bring that through there. And now I have enough information here, I can solve for the magnitude of AC. And so AC is equal to 0.46188 meters per second squared. And I got a positive number. I defined that as, I guess I never did put this, acceleration of c going in that direction. I defined it as going in that direction. I solved for it, got a positive number, so it is indeed accelerating up the hill in that direction. All right, what about the alpha term? Alpha of BC, which is right here, I defined it as positive going in that direction, in the counterclockwise direction. So let's solve for that in my equation. I got, look for the j's, AC sine theta, or sine 30, that's the first term on this side of the equal sign. And I go to the next side. That's an I, so the minus 7.2j comes down here. And I got a positive 0.8 alpha, which comes in there. That's the I term over there. So I'd already solved for acceleration of c, so I plug that into here, and the only unknown left is alpha. And so I get alpha is equal to 9.289 radians per second squared. That was a positive number, so it agrees with my sign, or agrees with the way I drew my arrow. All right, so those are the last two pieces of the puzzle that we were trying to solve for.